Forces 5 is about momentum, some key ideas in this momentum. Now, how do you work out the momentum of something? It's just mass times velocity. It's measured in kilogram meters per second. Don't forget it's a vector quantity. It has direction. So the momentum of a bloke on a motorbike is going to be 3,600 kilogram meters per second. Now, the momentum of an object isn't particularly interesting, not particularly useful. Momentum becomes useful when we consider the total momentum of a system of several objects, because there's something very interesting, very important about that. Consider this: from Newton's third law, the forces on these two trolleys is equal and opposite. Okay, trolley A and trolley B. So if they push against each other, the force is the same, the time of contact is the same, and so from Newton's second law, F is delta mv over t, then the change in momentum must be equal and opposite. So if one of them gains momentum, the other one loses momentum, and so the total momentum must be the same. So from Newton's third law, we get something called the principle of conservation of momentum. The total momentum of any closed system must be constant. Momentum is conserved. A very important idea in physics. Here's a simple trolley question, very kind of a multi-choicey kind of question. These two trolleys collide and stick together. Calculate the velocity of the combined trolleys immediately after the collision. Now, the way we go about doing it is we start with momentum before equals momentum after, as in the total momentum. The total momentum before is just 1.5 times 2, and then the momentum after 4.5, because it's the combined mass, times v, and that will give v is 0.67 meters per second. Here's one for you to do. It's a little bit trickier because now the trolley on the right, I'm saying, has a negative velocity, so it will have negative momentum. So work out the velocity of the two trolleys after the collision if they stick together. So as before, momentum before equals momentum after. So total momentum, notice one of them is negative now, and we get a velocity of 0.13 meters per second. There are two types of collision. There are elastic collisions and inelastic. In an elastic collision, kinetic energy is conserved. In an inelastic collision, it isn't. In these trolley collisions, they're certainly inelastic. We're going to lose kinetic energy. It'll be transferred into internal energy or heat, work done kind of crumpling the trolleys, perhaps a little bit of sound. Elastic collisions, later on when we do nuclear physics and we're talking about kind of particles getting close to each other, not actually touching each other but repelling each other and kind of moving off in different directions, like alpha scattering. Also in kinetic theory, gas molecules in what we call an ideal gas, we assume that all of their collisions are elastic. We assume that the total kinetic energy of these particles is constant. Anyway, if we look at this trolley example we did before, and what we'll do now is we'll work out the total kinetic energy before works out at 3 joules, the kinetic energy after works out at 1 joules. So kinetic energy has been transferred into other things. You can't say kinetic energy is lost, really. It has been transferred. I mean, energy is conserved. And it's probably been transferred, most of it, into heat, internal energy. Recoil, another application of momentum, is if this cannon fires a cannonball, the cannonball will gain momentum in one direction, the cannon will gain momentum in the opposite direction, and we can work out the recoil velocity of the cannon. Okay, if we say the total momentum before is 0, so the total momentum after is 0, and we've got the recoil velocity of the cannon. Vehicle propulsion. Now, this isn't really conservation of momentum, it's using F equals delta mv over t. The pump on this jet ski emits 20 kilograms of water every second at a speed of 25 meters per second. What will the thrust force be acting on the jet ski? So as I said, F equals delta mv over t. What we say is how much momentum does the water gain every second? And the momentum gained by the water every second will equal the force acting on the water, which will be the force acting on the jet ski, and that will be 500 newtons in this case. A very important idea, F equals delta mv over t, so Ft equals delta mv. This quantity Ft is called the impulse of a force. The impulse of a force can be measured in Newton seconds, and it is equal to change in momentum. Ft equals delta mv. In any collision, a graph of force against time is characteristically this kind of a bell shape. Okay, the force gets bigger, it reaches a peak, then it goes down. The average force is about half of the maximum force. This is a typical force against time for a collision. The area under a force time graph equals the change in momentum, which perhaps you can see from the equation above. Now, for these two graphs, the change in momentum is the same. However, because on the second graph the time is much bigger, then the average force will be a lot less. And if you can increase the time over which a collision takes place, then the average force will be smaller for the same change in momentum. If you jump out of a window, would you rather land on concrete or comfy cushions? And personally, I would rather land on comfy cushions. It'll take longer to slow down, the maximum force will be smaller, it won't break my bones. Practical applications of this, a lot of them are to do with safety in cars. If you wear a seat belt, or if you have an airbag, or if you have a crumple zone, then the time it takes for you to slow down and stop, let's say if you hit another car, will be bigger, so the average force will be less.